Hello all. So we are starting our second chapter, and which is origin of quantum theory. Our first chapter was all about classical mechanics and how Lagrangian equation, virtual work, how those equations we can use for different system. And we have seen system like pendulum, Atwood machine, and some other systems. So I think so that you have better understanding that what is classical mechanics and how it helps to solve some system or some problem in our day-to-day life. Now, the as name suggests, our second chapter is origin of quantum theory. Means this chapter is all dedicated to the origin of quantum theory. Means at what point classical theory fails and how quantum theory emerges, and who are the people who built this theory. So let's start our second chapter, which is origin of quantum theory. As I told you, this chapter tells us about how classical mechanics fails to explain some phenomena. So our first point is failure of classical mechanics. And what is it tells us? It tells before 1900, classical physics that is based on Newtonian mechanics could explain most of the phenomena. The motion of mechanical objects which are observable directly or with the help of simple instrument could be explained satisfactorily using simple equations based on the laws of classical physics. This all we have seen in our first chapter. Thus, classical mechanics explained successfully the motion of bodies moving with non-relativistic speed. Now, what is non-relativistic speed? It is the speed which is much less than speed of light. The discovery of electron by J.J. Thomson led to exploration of atomic system. So, in between 1900 there was a discovery of electron, and again there in 1905 Einstein had published his paper on relativistic motion or theory of relativity. So those are the two new point which had come in 1900. The first one was discovery of electron, which have gave us a new eye to see a very minute object, and the other one is theory of relativity, which tells us about if a object moves with the speed which much greater or really close to the speed of light, then how it behave. And scientists have observed that when people try to explore those system which comes under a microscopic system or relativistic system, then classical mechanics failed to give proper answer. So what are the field where classical mechanics fails are stability of atom, second one is atomic spectra, third one is black body radiation, fourth one is specific heat, fifth one is photoelectric effect, and sixth one is quantum effect. So these are six phenomena where classical mechanics fails to give proper answer, and because of this a new theory is necessary, and that theory is nothing but quantum theory. Now from which point quantum theory start building? So that is black body radiation. By studying black body radiation or by improvising theory of classical mechanics for black body radiation, a new laws have established, and those new laws are nothing but pioneering laws for quantum theory. Now what is black body radiation? Here our second point starts, and that point is black body radiation. So what we study under black body radiation? So here the issue is how radiation interact with matter. Matter means object, radiation means wave. How wave interact with particle? That is the basic question here. When heated, a solid object glows and emits thermal radiation. We all know that if you heat a iron rod, then its color changes. If the iron rod have silver color, when you heat it, its color changes to red, then yellow, and then it becomes whitish. As the temperature increases, as I told you, the object becomes red, then yellow, then white. The thermal radiation emitted by glowing solid object consists of continuous distribution of frequencies ranging from infrared to ultraviolet. The continuous pattern of the distribution spectrum is in sharp contrast to the radiation emitted by heated gases. The radiation emitted by heated gases has a discrete distribution spectrum, a few sharp narrow colored lines with no light, or that is darkness, in between. The same phenomena you have seen in your second year. We have that experiment with prism. You have a mercury source, and when you see through prism, you see some discrete lines of color. So that is what we have called it. We have called it a discrete spectrum. But if you see some heated object under that prism, then you will find that there is a continuous spectra. So that is the difference in a heated gas spectra of heated gases and spectra of heated body. Heated body gives us continuous spectra, and heated gas gives us discrete spectra. So there are two kind of spectra. First one is discrete spectra, and the other one is continuous spectra. Now, how radiation interact with object? When radiation fall on an object, some of it may get absorbed and some may get reflect. An idealized black body is a material object that absorbs all the radiation falling on it and hence appear as black under a reflection when it illuminated from outside. Means you all know that if I shine some object with some light, then some of light will get reflect. If it is a mirror, then 100% of light get reflected, and if it is some dark object, then some of the light get absorbed and some of may get transmit and some of may get reflected. Now, as this name suggests, black body radiation. So what is a black body? So black body is an object which absorb all of its radiation. Means if the you all know that the addition of reflectance, transmittance and absorption, the addition of these three factors equals to 1. But in case of the black body, the absorption phenomena is equals to 1 and the other two have value equals to 0. It means if I shine some black body with some radiation, then all of its radiation get absorbed by that black body. So that is a black body. So you know that how we see object. If some radiation falls on that object and that radiation again comes on your retina, then we can see that object. Otherwise that object will appears as black. The same feeling you have in night. If you switch off your light, then everything will appear as black, and that is because there is no light to fall on your retina, and that's why you see dark. Same happens with black body. If there is no radiation coming out from that object, then that object appears as black, and that's why it has name as black body. When an object is heated, it radiates electromagnetic energy as a result of thermal agitation of electrons in its surface. The intensity of this radiation depends on its frequency and on temperature. The light it emits ranges over the entire spectrum. An object in a thermal equilibrium with its surrounding radiates as much energy as it absorbs. As I told you, a black body radiates all the radiation which absorbed by that body. It thus follows that a black body is a perfect absorber as well as a perfect emitter of radiation. So you all know that once some threshold points appear, then that body has to emit those radiation to come to equilibrium state. So a black body is a 100% absorber as well as it is a 100% emitter. A practical black body can be constructed by taking a hollow cavity whose internal walls perfectly reflect electromagnetic radiation, as it is shown in this figure. So we can construct a perfect black body by this geometry. Radiation that enters through the hole will be trapped inside the cavity and gets completely absorbed after successive reflection on the inner surface of the cavity. Thus absorbs radiation like black body. So with the first strike, 100% radiation cannot be absorbed. So let's say if I radiate that object with some 10 unit of intensity, then in first reflection it will absorb 5 unit of intensity. So remaining 5 it will the second reflection will absorb 2.5 unit of intensity. Similarly, after number of reflections, there will be no radiation there appears there. So it can be considered as 100% radiation is absorbed by that body. On the other hand, when this cavity is heated, so that was the first scenario when we are shining that object with some radiation. Now the second scenario is that what happens if we heat that object. On the other hand, when this cavity is heated to a temperature T, the radiation that leaves the hole is black body radiation. So the radiation coming out from that hole is named as black body radiation. For the hole behaves as a perfect emitter. As the temperature increases, the hole will eventually begin to glow. To understand the radiation inside the cavity, one needs to simply to analyze the spectrum distribution of the radiation coming out the hole. In what follows, the term black body radiation will then refers to the radiation leaving the hole of a heated hollow cavity. The radiation emitted by black body when hot is called black body radiation. So this is the spectrum of black body radiation. So how we have to read this spectrum? As you can see that on the x-axis you have wavelength and on the y-axis you have energy distribution, or you can say that energy density. As you can see here, number of lines are drawn. With each line some specific temperature is given. It shows that as we increases the temperature, some different kind of spectra we observed. Now again, one notable thing is that as you increases the temperature, the maxima of the intensity shifted to the left. So at the very less temperature, you see this curve. This curve starts with means the starting of this curve is under red color, means the wavelength of red color. So when let's say some body you heated with this temperature, you see that body as a red. There are other radiation also which are emitted by that body, but as you all know that we can see only a specific spectrum of light. Our eyes can only see 300 or let's say 400 nanometer to 700 nanometer of radiation, means wavelength of which comes under 300 nanometer to 700 nanometer. So as you can see here, radio waves and other waves are also emitted by that body, but as we are human, we cannot see those radiation, and that's why that object appears as red. Now this second spectrum, as you can see, if some body is heated with this temperature, then as you can see there is a maxima of that spectrum is at this point, and the lower part has included yellow color as well as red color, and so if you see that body, it will appear yellowish. As you can observe, if I increase the temperature, then more color of the visible band comes under that spectrum. It means that initially at a lower temperature you can see only red light. As temperature increases, red plus yellow light you are able to see. Again, if we increase the temperature, then bluish color also comes under that spectrum. It means that at very high temperature, all the visible color can be emitted by that body. And again, you know that the addition of all color is nothing but a white color, and that's why at very high temperature that object appears as white. Okay, so that is the reason why when we hit some body, why after some time it appears as white. Okay, so that is the spectrum of black body radiation. Now there was some scientist, the first one is Wayne, who tried to explain radiation coming out from that black body or the continuous nature of radiation by some laws. After that, there is another scientist whose name is Relay Jean, and he also tried to explain why we see continuous nature and how we can fit this spectrum by some equation. But those two have not completely described or succeeded to explain those spectrum. So after that, a third person came to explain this spectrum, and he was Planck, which he totally succeeded to explain how this spectrum emerges. And all you know that the pioneering postulate of the quantum mechanics was established by Planck. So on the basis of his postulate, complete quantum theory is based. So we stop here, and in next lecture we will see how Wayne and Relay try to explain this black body spectrum. Thank you.